for you the story of how I reached where I am today actually. So I have been born in a really small city in the north of Iran, in Babol. It is close to the Caspian Sea. I have studied my bachelor degree in power electronic engineering in Babel University of Technology. After that, I moved to Isfahan as one of the most beautiful cities of Iran. And I studied my Master of Science in Isfahan University of Technology in control engineering. After that, I started to work as a researcher in incubation research center in one of the universities in Iran, and at the same time I was actually teaching also a bachelor course in one of the university in computer engineering in Iran. So being always in an academic environment, in a research environment, made me to be interested to start a PhD program, and that is why I started to search online on the website for available positions in Canada, in America, in Europe, and that's how I actually met and sent an email to Professor Stepone in the CAD and Reliability group of Politecnico di Torino. And I was lucky enough that he actually read my email between thousands of emails that they're receiving every day, and we started online collaborations that actually 6 years ago, it is not like COVID time of today that it is so much common. So 6 years ago, we started an online collaboration for almost 8 to 9 months. We reached to publish a journal together, and after that, I applied for a PhD program in the computer department of Politecnico, and I started my PhD program in November 2015. So I moved to Italy, and I started and I became a PhD candidate. In May 2019, I finished my PhD program, and I did my PhD thesis. Actually, I had the chance to participate in many competitions. I won the best PhD thesis of the computer department. I have won the best PhD thesis in Europe, always in the fault tolerance and reliability, and so many other competitions. And after that, after graduating from my PhD, I decided to continue my research in the same group, in the CAD and Reliability group. And since then, since May 2019, I am a postdoctoral researcher in the same group, in the Computer and Control Engineering department in the Politecnico. And basically all these years, all these 5-6 years, I dedicated my research to prove that there are invisible things that matters, and they are going to affect our life and cause a failure in our life. So we need to take into account these invisible things, and most importantly, we need to prevent from them to happening. So let's start from the really source of the problem. What are these failures that I'm talking about, and how is the effect of these invisible things in our life? Imagine to be sitting in an airplane, relaxed, comfortable, hopefully rich enough to enjoy a glass of wine and so on, and suddenly our plane drops down. This is what happened in flight Qantas 72 in October 2008. That was going from Singapore to Australia, that the flight suddenly dropped down. So basically after 3 hours that the flight started, the plane dropped down for 200 meters in 20 seconds, and this happened twice. So the flight needed to have an emergency landing. And of course, as you can expect, many people got injured. For sure, they from bumping their head to the ceiling, and they end up in a hospital and so on. But what happened to that airplane? As we all very well know, outside the Earth, it is the atmosphere it is the environment full of radiation particles that is known as space radiation particles. This particle can pass from the Earth's atmosphere and cause basically ground level radiation. So when we are talking about the space radiation, or even when we are talking about the ground level radiation, these particles can interact with our devices, with our electronic devices that is used in a spacecraft or in an airplane or even in our computer and smartphones, and cause failure and cause radiation-induced effect in our electronic devices. These radiation-induced effects these radiation effects are basically categorized in two groups. The first one is cumulative effects that is happening due to the accumulation of these effects. For example, when you expose, it is totally dependent on the exposure time of the device toward the radiation. So It can create several effects. For example, a typical effect that a cumulative effect can have on an electronic device is degradation of the performance. So the device becomes slower and slower by time. We have another kind of effect that is called single event effect. So it is an effect of one single particle that is crossing our device, an electronic device, and it might cause a failure or an effect in the device. Okay, so it is an effect of one single particle, and it is totally independent from the exposure time of the device. If this single particle creates an effect that is not able to recover and damage the device permanently, it is called as hard errors. While if this effect is lasting for a period of time and you can recover from it, for example, by repowering the device, it is called soft errors. That depending on where this incident is happening in our electronic device, it can cause different kind of effects. For example, if this radiation particle is hitting a memory or a sequential logic of a circuit, it can change the state of this memory from 1 to 0 and 0 to 1, that eventually it can cause a failure of a spacecraft or an airplane, as we saw. On the other hand, depending, for example, if this radiation particle hits the combinational logic of a circuit, it can create a voltage glitch or an undesired voltage glitch in the circuit. That is known as single event transient pulse. But this pulse itself is not a failure, or it is not a critical issue for our electronic system. If this pulse propagates through several paths of the circuit, it reaches to several storage elements, for example, several flip-flops of the circuit, it can change the state of these elements, these storage elements, and eventually it can again cause a failure and malfunction of the total system. When we are talking about this transient or single event transient in recent days, it is even becoming more complex. Why? Because we are dealing with technologies that are becoming smaller and smaller every day. So it means that even if we have a particle that has a really low energy, it can change the node's voltage, and it can create a voltage pulse, an undesired voltage pulse, or an SCT pulse. From the other side, we have the recent applications that are crazy, and they are becoming faster and faster every day. So basically, there is more probability for these pulses to be captured and to be sampled in the fast circuits that we have recently. So basically, the sensitivity of our current systems is even higher and becoming higher every day regarding these transient errors. So knowing these effects, let's go to see what happens in the flight computers of the quantas that actually cause that unfortunate phenomenon. So computers are running based on the string of binaries. So all this operation and all the information are transmitted based on bits and based on strings of binaries. That to each one of these bits, a transistor is dedicated. So you can transmit different information. You can do different operations by turning on and off these transistors. So basically changing the state of these bits from 1 to 0 and transmit different information. Now, if we have a radiation incident, if we have a particle that hitting one of these transistors, it can change the state of this transistor from 1 to 0 and 0 to 1, and basically cause a wrong output or a transmission of a wrong data and wrong information. This is exactly what happened in Flight Quanta 72. So in the Air Data Inertial Reference Unit of this airplane, there was a 32-bit that was actually responsible for critical data, for example, airspeed, altitude, and so on. So this 32-bit was divided into two groups. The first 8-bit was representing the data label, while the second 24-bit was representing the data itself. What does it mean? For example, the first part, the first 8-bit was showing a number of 8 as an example, and this number was actually representing a label of altitude of the airplane. While in the rest of the bits, so in the other 24-bit, you could have seen the actual value of the altitude. There was an incident in one of these bits of this first 8 bits, so instead of transmitting the data, labeling the data for the altitude, it labeled the data for angle of attack, while the data that was represented was actually the altitude of the airplane. So the flight, the computer tried to recover from the wrong altitude that it was expecting, and that's why it dropped down and it caused that unfortunate event that we all saw. So this airplane was built, I think, in 1992, and there was no control and there was no standards regarding the radiation effect. Now we are dealing with semiconductor computers that are continuously developing shiny new products or smaller products, faster products. And from the other side, we have the space agency that, as you can see every day, they are going crazy with the new missions, with the new spacecraft that they are launching, and the quality system are really complex. So the question is that, are these new shiny products reliable enough to be used in a space mission application? Or are these devices able to tolerate faults that are induced by the environment? In another way, are they dependable enough to be used in mission critical application that basically if it goes wrong, a lot of money is going to be wasted? And that is what I have dedicated this years of my research activity to study. So what we are doing is studying from the really source of the phenomena, from the radiation environment, and investigate that, okay, we have this radiation environment, we know for this mission that is going in this orbit, these particles are expected, this energy for this particle are expected, and now with respect to the system that we have, which kind of event we should expect and which kind of transient pulse we are expected to observe in our system. And secondly, okay, now at the second phase we know that we are going to have these pulses, these features, pulses with these features. What we can do, are these pulses are going to create an error in our system, or we can just ignore them? Or if they are going to create an error, what are the possible mitigation solutions and techniques that avoid the failure of our mission and of our system and lead to a successful mission? And of course, the goal of all this activity is to apply them to real missions, that is real space mission, for example, and make sure that instead of failure of the mission, we are going forward to have more and more successful mission every day. So starting from the source of this phenomenon, we have developed a tool that is called radiator. That is actually dedicated for simulating the passage of these particles inside the silicon matter of integrated circuits and ICs. But it is also extended to a whole system. For example, it can be used for performing radiation analysis of a CubeSat, of the total CubeSat. So how this tool is working is, it is in a very simple way to explain about this tool. It is starting from the two-dimensional structure of our circuit, and then translate it into the 3D structure of the circuit that is implemented in our IC. And then performing a simulation that is actually executing of charge sharing, distribution, and propagation. So basically, radar is telling us that this particle is passing through this device, because we know that the 3D structure of this circuit that is implemented on this IC or on this device, it performs this simulation and it calculates, okay, if this particle is passing through this element, how much energy and how much charge is going to be released in each node of this circuit, and eventually it is converting the released energy into voltage. So basically, we started from an energy or a particle with an energy, we simulated, and at the end we know that regarding this radiation environment, with this implementation, physical implementation of the IC, we are supposed to expect these SCT pulses, this data set of SCT pulses with this duration and with this amplitude of the voltage. Now that we know that this is the pulse that we are expecting to observe with respect to our mission environment and our physical implementation of our device, of our circuit, okay, now it is time to study that, are these pulses going to cause a failure in our circuit, or is our circuit is going to work anyway well, and we don't need to apply mitigation techniques. So what we did that is we used an electrical circuit simulations, and we instrumented in this simulation basically by inserting the SCT pulses automatically in different part of different nodes of the circuit, and observing the output to see, okay, if the inserted pulse is going to create an error in our system or not. Just a really simple example of one of these application of this analysis workflow. I can mention a really simple circuit of a full adder cell that we are all familiar with. So what we did is we developed the layout of the 45 nanometer full adder cell, and we use simulation tool to analyze and to investigate and to estimate actually what are the SCD pulses that we should expect to happen with respect to the specific radiation profile and radiation environment. So we know that, for example, if we perform 10,000 particle evaluation, particle injection in our circuit, we are supposed to observe around 1,000 SCD pulse with this duration and this amplitude of the pulse. Then we went to use the electrical simulation, instrumenting an electrical simulation, and automatically insert the SCD pulse in different transistor nodes of a simple circuit. For example, here we are talking about full adder cell. So we insert the pulse in different transistor nodes, and we observe the output of this cell, of this full adder cell, to see, okay, if we insert the pulse, is it going to propagate to the output, to the sum and carry output of the circuit or no? And using this method, we observe that not all the transistors of a cell, for example, a full adder cell, has the same sensitivity. We saw that, for example, 4 of them are much more sensitive with respect to the other one due to the physical implementation and layout of the circuit. So we actually, for mitigation and for fault tolerance techniques, we focus on this specific sensitive transistor instead of focusing in all the cell together. Because, for example, as a normal mitigation technique is that, okay, you apply replication, you duplicate all this circuit, and you are able to, as a typical mitigation solution, no? But duplicating all the circuit means that you are duplicating basically the power consumption, you are duplicating the resource usage of the circuit, you are probably decreasing the performance and the speed of the circuit. So if we can identify the part of and the nodes of the circuit that are actually more sensitive, why to apply duplication to the all of the circuit and not just to the sensitive part that, for example, 90% of the errors are coming from these sensitive nodes. And that is what we have tried to do. So we identified that these 5 transistors are responsible for 80% of the errors that you might observe. And we applied mitigation technique. For example, in this work, we applied duplication to these sensitive nodes or this sensitive transistor that cause the sharing of the charge that has been transmitted by the particle. And actually, at the end, we observe a weaker SCD pulse that has a lower chance and lower probability to propagate to the output and create an error. But who is working with the simulation, electrical simulation, knows that it is not really fast. So even for performing a full adder simulation for 1,000 times, you need hours and hours of simulation. So when we are talking about complex circuit or about a spacecraft environment or a spacecraft circuit, it is basically impossible to apply techniques like this so much low level. So for sure you need, we need a higher level techniques and analyzing and mitigation tool to be applied to industrial circuits that have a huge amount of resources. And that's why we have dedicated some time to develop analysis and mitigation tool actually. So one of the tools that we have developed is single event transient analyzer or SETA tool that is acting on industrial circuits with huge resources, and this tool is basically starting with the netlist of the circuit and develop and create the graph description of the circuit or the physical design description of the circuit, and then it evaluates, it investigates the possibility of transient pulse happening in all the inputs and outputs of each combinational logics of the circuit, propagate this transient pulse that we inserted in all these input and outputs of the combinational logic until it reaches to the first storage element. So it basically investigates if we insert a CT pulse in these inputs and outputs of the combinational logic, is it going to reach and propagate to any flip-flop? and if it is going to reach to the first storage element, what is going to be the features of the pulse, so what is the duration and what is the amplitude of the pulse that is reaching to this storage element. Again, why it is useful to perform this kind of analysis? Because normally if you have a circuit, you are going to apply replication to all the storage element, to all the flip-flop of a circuit. But it has sometimes it is impossible, especially when we are talking about industrial netlist. It is huge. They care really about the speed of the circuit, so it is impossible to apply replication to all the circuit. So you need to identify the sensitive part, the sensitive flip-flop of the circuit, and go and target that actually element to perform a mitigation technique and fault-tolerant technique. And that is what we have done. So before applying a mitigation, we are analyzing that, okay, if there is a pulse in one of the inputs of this gate, it is going to propagate. For example, it is going to reach to a flip-flop B, it is going to create an error and probably sampled by this storage element. So what we can do to avoid this, one of these mitigation techniques that we can actually do is applying a filtering logic or a guard gate logic. So what we are doing is we are taking the netlist automatically. We have a tool that is automatically cutting the netlist before the sensitive flip-flops and insert the filtering logic or guard gate logic. So now if the same pulse affect the same point, the same nodes of the circuit, it is going to propagate. As soon as it's reached to this filtering logic, it's going to be captured or to be weakened by this logic structure, by the filtering structure, and our flip-flop is going to work healthy and safe, and we can avoid the failure of our system. So, of course, the goal of all of this research that we are doing is to apply these techniques to real applications and real space missions. So one of the missions that we are involved with together with our group is the Euclid space mission that has the objective and the goal to map the geometry of the universe, understand the mysterious dark matter, and so on. So one of the small netlists of one of the units of this Euclid spacecraft has been provided to us by European Space Agency, and we performed analysis and mitigation technique on this netlist. And a part of all that numbers that it is written here, so actually we were able to reduce the possibility of observing or of capturing the possible transient errors by the storage element of the circuit by 80%. Another interesting project that we are involved in is a HERA space mission project that is actually a first humankind's probe to gather scientific data to help scientists and future mission planners to understand the asteroid composition and so on. So in a good way, in an understandable way, what HERA is doing that, we saw some weeks ago that SpaceX launched a Dart spacecraft that was developed by NASA. So basically Dart is going to hit an asteroid that is called Didymos, and it is trying to change the orbit and the direction of this asteroid. This asteroid currently is far from us, so it is the first mission that humankind is doing, trying to reach to the future that we can defend the Earth. So in the future, if there is an asteroid that is going to be threatened for us, we can protect the Earth, and we can protect the Earth. So that's why NASA is trying this mission for the first time, to go and hit the asteroid and change the orbit and the direction of this asteroid. After DART, HERA is going to be launched. HERA is known as the sister of the DART, and HERA is basically going to take pictures to see when DART is hitting this asteroid, what happened, and send some pictures to the Earth so scientists can study and see what happened to this asteroid. So there is a CubeSat in this mission that we are working on. So basically we are working on performing a radiation analysis on the CubeSat that is called Milani of this HERA mission. And of course the question is that, okay, we are doing a lot of simulation tools, we are writing codes and algorithms in C, in Python, how we can trust this to apply to a real space mission. it is not exactly all simulation and coding. So we are doing some real experiment after working with simulation and tools that we are developing. So if we have a plain design that is without any mitigation technique, then we develop designs that has fault tolerance and mitigation technique inside, and we go to the radiation environment, to the radiation centers, to actually put the device in front of the beam, in front of the accelerated beam. That is the closest scenario that we can have with respect to what we have in the space. So we put the boards in front of the accelerated beam, and we observe what is happening in this device, in these designs, while the beam is attacking them and hitting these devices. And of course you see these beautiful pictures here that we put the device in front of the beam, but that is actually a lot of work. So it is like 2 months and months of preparation before going to the radiation center. So we work a lot as a team before going to the radiation test. So we do a lot of meetings, we prepare our design very well to make sure everything is going according to the plan. We do our original design, we apply different mitigation technique, we apply simulation and analysis tool as you saw before. So we make sure that when we are going to the radiation test, everything is working perfectly and we can actually evaluate the design that we are developing. And of course we arrive to the night before that it is always happening that nothing is working. So everyone become really tired, but we have the train and the airplane time to reach the radiation center to make everything work, and we arrive to our radiation center. When we arrive there, we need to mount our devices in front of the beam. So we have all the guide there to help us to mount our devices in front of where the beam is expected to be observed. This is the test that we have done 2 weeks ago in December, the first week of December. So here you can see Daniele that is actually trying to mount the devices that the FPGAs that has the design that we prepared before. And you should mount the device in a way that exactly the area of the device that you want to expose to the radiation beam is arranged, is in the same location as the beam is going to, is aligned as the same location as the beam is going to be expected. So this area that you can see is actually the beam room. We put the device there, we need to set up everything and then go to the control room that normally it is far from the beam room just to follow the safety and the security. But these devices that we are putting in the beam room, we are actually need to observe what is happening to them during the beam time. So basically all these cables that is coming out of the device, it is helping us for monitoring what is happening to the device when it is exposed to the radiation particles. That's why Andrea is trying to pass all these cables that is coming out from the devices from this hole to reach to the control room where we are seated and we plan to observe our device. This is the overall view of the beam room. That is this here, you can see it is where the beam is expected to come out, and we have aligned our devices exactly in the location where we wanted to expose to the particles, exactly where it has been represented by these lasers that okay, the beam is coming, is going to be here. So we aligned our devices to make sure that the area of the device that we would like is exposed to the radiation particles. Then these cables, all these cables that you're seeing from coming out from the FPGAs are passed through the tunnel and it reached to the control room that is, it is 25 to 30 meters in distance from this room. We close the beam room and we are going to the radiation room, to the control room. So you close the beam room, the beam is going on, and you go to the control room, and basically here you can see these three, that each one of them is responsible for one of the devices that we place in front of the beam. So they are observing the devices all during all the experiment to see what is happening, is the device is broken or it is going well, the experiment and so on. We have Daniele here that is sitting in front of these many monitors. That is actually the guy who is responsible for configuring the beam. So if you have 8 or 10 hours of the beam time, for each 10 minutes, each 15 minutes, you need to configure this beam. So you can say that, okay, now I want to have a run for example, 10 minutes. I want this number of particles, and I want particles with this energy. And that is how we are communicating with our beam, and we are telling to the system which kind of configuration for the beam we would like to have. And a person is needed to actually decide which kind of configuration we need. And this was my role in the last test that we have performed in PCR radiation center. So there is a bridge. There should be a bridge between these two groups. So at the moment you should check what you're observing in your devices, and based on your result you should decide for the next round that which kind of configuration for the beam you would like to have. And that was the role that I was carrying on in the last experiment. So as a university, we are always waiting for a European Space Agency or for other companies that we're working with to actually offer us some beam time. And normally the beam time is offered to us from 7, 8 o'clock at night until 7, 8 o'clock in the morning. So we are passing basically 24 hours of not sleeping and not resting, and this is sometimes really challenging to keep ourselves awake or actually to be a nice person. And all of us pass some moments like this that we had difficulty to follow our boards and follow our role during the experiment. But at the end, when we are finishing the experiment with hands full of numbers and full of experiments, we are actually coming back home with happy faces and with a successful mission and experiment. After coming back home with these results, it will be time to share these results with the community and with the expert to actually have feedback from them. That's why you need to publish a result, or you need to go to the workshop, to the conferences, to actually share the result to see what is the feedback of the expert in the community. I had the chance to go through a lot of these places in this workshop and these conferences, and one of the best experiment I had was the workshop that was in European Space Agency. That was actually, this room is room full of experts, really the experts of the topic from all over the world, and I had the chance to present in front of them and have like good and also bad feedbacks on the research activity that I was carrying on at that moment. And of course, all what I have explained to you is not a work of one person. I'm part of the aerospace and the configurable computing team. I was lucky enough to be inside a really nice team. Actually, my supervisor, Professor Sterboni, is always, when he wants to introduce us, he's saying, okay, this is my team, and they are nice people, so sono simpatici. So I'm going to repeat what he's saying. We are in aerospace and a configurable computing team, and we are nice and hardworking people. If you like our topics, please contact us, and we will be really happy to welcome you to our group. Thank you for your time.